everybody. Thank you so much for coming. If you are unaware, this is our final installment of the fall 2025 lecture series. So thank you so much for coming. As you may have noticed, this lecture is a little bit different in the fact that while we normally only have one speaker, this time we have three, all three of which are some of our CAS undergraduate seniors. So our speakers today are going to be Hounan Gong, Ella Mansfield, and Abigail Bull. So we are going to start with Hounan, and I hope you all enjoy. Please welcome Hounan Gong.
Let's start a timer here in case I go too long. So today we're going to be talking about this moon called Io. Io, in case you don't know where that is, our nice solar system. We're right here, and Io is a moon that's orbiting around Jupiter, which is right here. So we have a little Io, not to scale in this diagram, but it's orbiting around Jupiter. And I'm splitting my presentation into two parts. I mainly want to spend time on part one because I want to talk about why volcanoes on Io are cool in general. And then I'll move on to part two where I'll be talking about my research on Io. So why do we care? Well, let's first talk about volcanoes in general and why do we care about them? First and foremost, they do directly affect our lives. About 800 million people in the world live within 100 kilometers of an active volcano. I think in the US, the most prevalent incident of this happening was Mount Helens in 1980, which erupted in, Mount Helens is, I think, 120 kilometers away from Portland, Oregon. So very close to a major city, massive eruption. I think 57 people died, thousands of animals died, lots of infrastructure and agricultural destruction. More recently, we have this that happened 2 days ago in Mount Semeru in Indonesia. Now, I bring all this up. I mean, obviously, Io's volcanoes aren't directly infecting us in this way, but I just wanted to show these just to give you a sense that volcanoes are very massive enactors of change on any planetary surface. They can do a lot. They are very powerful. You can see that on Io actually right here. So this is Io, and we have the moon for reference, and you can see the volcanoes even just visibly from the picture massively change the surface of Io. So first and foremost, it is yellow. That is a very interesting thing. That's due to sulfur that the volcanoes on Io are spewing into the atmosphere that then fall and make an icy coating, a frosty coating across the entire surface. So that's one thing. Another thing that I find even more interesting is that just also give a reference, all the black spots that you see on Io are where the volcanoes are. Other than those spots, it is mostly smooth. You will see that there's actually no craters like you have on the moon. And that's because the volcanoes are spewing up so much material that it's making a new surface just continually. It's like a snake shedding its skin. It's just continually resurfacing new material on the surface. Any crater that was there would have been piled on by volcanic activity. So you can just visually see volcanoes are just actively changing this. Some other reason why volcanoes are interesting. For geologists, they are a window into the interior of the planet. So volcanoes work in that they bring magma from deep under the crust and the mantle and bring it up to the surface. And that's really useful because normally we couldn't get that material from deep in the crust and the mantle normally, but the volcanoes are just bringing it up for us that we can study, and we can use that to study the interior planetary structures. So it's like my analogy is like like a doctor taking a blood sample. Like they need to take blood from within you to understand your internal biology. And the final thing that I'm going to talk about why they are useful is planetary scientists. They will help us find life possibly on Europa, which is a neighboring moon also around Jupiter. And before I go quickly into that, just a brief thing about tidal forces and tidal heating. Tidal heating is what causes the volcanism on Io. And that tidal heating is due to the orbital dynamics of Io orbiting around Jupiter. It is in orbital resonance with two other moons, Ganymede and Europa, all orbiting around Jupiter. And the tidal forces from those other moons are what leads to that tidal heating. Tidal forces, the main thing that you guys will probably know it from is the moon enacts tidal forces on us, and that creates the tides that we see on Earth. But those tidal forces on Io are immense. They're immense tidal forces. They create an immense amount of internal friction, and that generates the magma and the volcanism that we see. And I bring this up with respect to Europa because if Europa is enacting tidal forces on Io, the reverse is also happening. And that's specifically interesting for Europa because the current theory of Europa is it might be able to harbor life in a subsurface ocean underneath an ice shell. And the way that that life might be sustained is due to energy from tidal heating. So if we better understand tidal heating from Io, we can also understand tidal heating on Europa. And Europa is obviously of very big importance to NASA, for example, who has the Europa Clipper mission that is set to arrive at Europa in 2030 and possibly try and find signs of life there. Anyways, so we talked about why we like to study volcanoes in general, but why are Io's volcanoes specifically so unique? Why do we like them so much? Again, back just setting the scene. It's here. It's orbiting around Jupiter. Volcanism is not too common of an occurrence in the solar system. There's only a few other places that have it, and I'm going to highlight a few. We know that one. Earth, yes. Venus actually technically does have the most volcanoes. It has 85,000 volcanoes, but most of them are dormant, so we're not really going to talk about that too much. And then Enceladus is an example of a moon with cryovolcanism, but not lava volcanoes that we're going to focus on here. So generally, other than Earth, Io is the only other place with extensive active lava volcanism. And now I just want to do a little comparison between the two, between Earth and Io volcanoes. So in terms of pure numbers, Earth's got Io beat. It's got 1,350 volcanoes, while Io only has 400. So even though it does have more volcanoes, the main thing is that Io is a lot more volcanically active. This is a pretty old graph. The numbers might not be correct now, but the general gist is true in that the amount of magma or volcanic output on Io is much larger than that of Earth. And also to note that these are the correct relative sizes of the Earth and Io with respect to each other. So something that much smaller producing that much volcanic activity is pretty cool. Comparing some specific instances or specific volcanoes between Earth and Io now. So we got the tallest volcanic plume on Earth. The plume is essentially when a volcano erupts, the massive spew of materials into the atmosphere. The tallest one recorded on Earth was by the Tonga volcano, which is an underwater volcano that had a plume towering at 57,000 meters, or 1,075 McGraw towers. Now comparison with the largest volcanic plume on Io, which is from a volcano called Pele, towering at 300,000 meters, which is 5 times taller than the previous one, than the Tonga volcano, or 5,375 McGraw towers. I would like to point your attention to this GIF right here from the New Horizons spacecraft. I think it's super cool. It might be hard to see from the back, but right here, you can see the volcanic plume from Io. You can see it literally come off the surface and dome over and fall back down. And it's like, you can see its magnitude compared to Io. It's really big. Another example about lava lakes. So the largest lava lake on Earth is the Mount Nyiragongo in the Democratic of Congo. See, right, some nice pictures right here. The crater has a diameter of 1,200 meters, or 20 Appel dining halls, which you're sitting in. Trying to come up with fun units for this. And for comparison on Io, the largest, they call it a patera, but a patera is basically a lava lake. It's 202,000 meters, 200 times as large as Mount Nyiragongo, or 4,000 Appel dining halls. Anyways, yeah, I just would like to, volcanoes on Io are very, very interesting in that they're so extensive compared to Earth. But the thing that geologists like to study specifically about those volcanoes is, okay, we know 100% sure tidal heating is what causes the volcanism that we can see on the surface, but there's a lot of stuff in between that initial tidal heating to the volcanoes that we can see on the surface that's happening. A lot of geology under the surface that we don't know that much about, and we want to try and learn more about it. This is a lots of words on this, but you don't really have to worry too much. This is just showing different possible models we have of the interior structure of Io. It could have a magma ocean. There could be a sort of magma sponge structure underneath the surface. The reason why there's so much talk about this is basically and I'm simplifying a little bit, but there's this this contradiction where basically something I haven't said before, but Io also has very, very tall mountains. Like its tallest mountain is like twice as tall as Mount Everest. Very tall mountains. In order to have very tall mountains and stuff like that, you have to have a very thick crust or lithosphere to support that structure. But we've already said before that it also has a very, very large amount of volcanic activity, which means it needs a lot of ways for magma to get from the inside to the surface. And then that's where the sort of contradiction comes, where it's like, okay, you need a really thick crust, but that contradicts the fact that we need a lot of magma going through to the surface, which would be hindered by a very thick crust. And so the modeling is trying to figure out how we can have sort of both of these at the same time, but that's a simplification. But anyways, in conclusion, volcanoes are super interesting. I have 5 minutes left to talk a little bit about my research. So the big question in my research is this: is there diurnal tidal control on Io's volcanism that is distinct enough to be discerned from the eruption process and be detected by remote sensing data? Basically, all of that means this, where basically, okay, we know Io's orbiting around Jupiter, and we know that the tidal forces have a cyclic pattern, and the period of that cyclic pattern is equal to however long Io takes to orbit around Jupiter, which is 1.77 days. So we know that to be true. And we want to see if the volcanic activity reflects that. We want to see if it also has that cyclic pattern. We have not found that yet. We found that for other moons. We found that for Enceladus, for example, that its plumes are tidally controlled. We have not seen that for Io, and it's partly because Io has, as I said before, it has very interesting internal geological mechanisms that we don't know too much about. So in summary, basically, we want the data that we get of specific volcanoes on Io, we want it to follow a sinusoidal pattern that matches, that has a period of 1.77 days. That's basically the big, if there's one takeaway about my research, it's this. This is what I'm trying to do, basically. But there's a lot of steps to get to it. The main first thing is getting a lot of volcanic data. So we do have a lot of volcanic data of Io, but it is scattered in a lot of different places, taken by a bunch of different telescopes. Currently, well, up until this project, we didn't have a combined data set of all the emission data from Io, from all different sources. And so that was sort of the first half, was getting that. So these are the 4 sources of telescopes that we got data from. 2 ground-based telescopes, so Keck and Gemini, and 2 space-based telescopes, so Galileo and Juno, actually went to Jupiter and took some measurements there. A lot of processing data that had to be done. I'm not going to go through that. Basically, we made the data set. We had, the number is blocked, but it's 8,203 thermal emission observations across 274 hotspots. And when I say hotspots now, hotspots basically means volcanoes. There's like some nuance, but for the purposes of this, hotspots means volcanoes. And this is the current map of Io, and the labels are really small for you guys to see, but trust that all the volcanoes are labeled on this map. Here are some examples of emission data we had for 2 specific hotspots or volcanoes. We have Loki Patera on the top. That was the volcano that I talked about before. That was the largest lava lake on Io. And so we have nice data that was taken all the way back in 1996 up until 2024. Janus Patera is another example of a hotspot that we have nice data from, a good decent data from. And basically the crux of what we needed to do was we needed to use something called the Lomskargel periodogram, which is basically, it's just a mathematical function. I won't get too much into it, but it turns the figure that you had before, where you have observations plotted across time, and we want to turn that into something like this, where basically this is telling you, okay, we're trying to see which, the x-axis is frequency, and we're trying to see which frequencies the data is most likely to be oscillating at. And our research question is, we wanted to find if it was oscillating at 1.77 days. So naturally, we try and find a peak at 1.77 days, right? I guess this is frequency, so it's 1 over 1.77. But that's right here, and we do also have a nice peak there. So that's very nice, actually. But we have to do that for all the hotspots that we have, doing a bunch of stuff. The main 10 that we sort of found to have very significant patterns of tidal modulation were these 10 listed over here. Yep. Another thing, oh, I'm running a little bit out of time, but another thing that we did was we also tried to correlate the observations with some models of the tidal forces. So we can't exactly measure the tidal forces, but we can guess what the tidal forces, the cyclic pattern of the tidal forces might be. We used this nice 4-layer model and did some numerical modeling to calculate tidal forces. And again, just back to the big question. So the additional stuff here is basically now we have modeled the tidal forces. So pretend that we had a nice model, a sinusoidal curve of the tidal forces. We want to see if it correlates with the data. And so we did a bunch of stuff with that, but we weren't really able to find too much correlations. So we were only able to find the green dots are all of the hotspots that we found significance with respect to the tidal modulations. And then the blue and the purple are two different models that we found these hotspots to be correlated with. And I'm realizing I'm running out of time right now, but yes. So in conclusion is we found those sets of hotspots that were significant with respect to either the model or just generally a cyclic pattern with a period of 1.77 days. Some caveats, just some random caveats. I'll just skip over those. But yes, these are my acknowledgements. Mainly, I would like to thank Ashley Davis from JPL and Catherine DeClear from Caltech, who have been my primary mentors throughout the 2 years of me working on this project, and they have been wonderful mentors. Yeah, thank you.
Okay, so the way that we're doing Q&A, if you are used to these lectures, is a little bit different than normal because we have 3 speakers. So instead of one long Q&A session at the end, we are going to have 3 really short ones. So if anyone has any questions about Haunen's research, now is the time to ask. And please feel free to ask anything. Yeah, we're also going to be switching over. Yes, let me come over to you.
Yeah, can they detect tidal forces on volcanoes?
And they detect, can what detect? Sorry.
Scientists detect
Yes.
influences of the tidal movement or influence of the tide in any way on volcanoes on Earth.
The Earth is a little bit also complicated as well because there's tectonics that are involved in it, so it's not exact. We can't exactly find it exactly. But
Thank you.
yeah, Earth is also itself a very complicated geological planetary body.
Do we have any other questions? I also forgot to mention chat is enabled on the Zoom. If anyone on the Zoom has any questions. Yes.
Thank you for the talk. I'm just kind of curious about, so I know you found those 3 peaks in the graph, and
The periodic.
yeah, that's right. And I'm curious as to why, what explains that variation, why they are all very clearly associated with one. Like, why are there certain locations that are different than the rest?
You're asking about, oh, I guess it's
Right,
switched,
so
but
you had
the
the
periodogram with
the
the peaks of
Yeah.
frequency.
Yeah.
The other peaks of frequency are primarily explained by um, it's a mathematical result of the alarm-cycle periodograms in that if there are observational biases such that, you know, if you have a telescope on Earth, it can only take data from Io at specific intervals just because the Earth is spinning. So in addition to just the mathematical way that the alarm-cycle periodogram is done, the other frequencies are basically either multiples of the relevant frequencies, so higher harmonics of that frequency, or multiples of Earth's diurnal frequency, just purely because, you know, if we took data, yeah, we're taking data on Earth, so you will naturally see increments of like 24 hours in the data, just because that's when we take it. Yeah, those show up in the periodograms. That's a very good question. Yes, that is one of the next steps that I sort of skimmed over. But right now, the main thing was looking at individual volcanoes and seeing if they have any tidal control. But we can also, for example, take a bunch of volcanoes that are grouped around the same area and just thinking about it. Those should have very similar cyclic patterns because they're right next to each other. And that's also something that we're looking into right now.
Any other questions? Okay. I don't know if you guys have noticed we are experiencing a few technical difficulties, so apologies for the delay. Are we maybe good? Okay, yes. Our next speaker is Ella Mansfield. We're gonna follow a similar, hopefully, process where Ella will give her talk and then we'll have a short Q&A. And hopefully the audio will stop cutting out. Not working? Hold on, get rid of those things on the side.
Yes. I'm kind of incompetent at this. Well, I don't know how to make it go away. I've been Hi guys, can you hear me? Cool. I was gonna have a nice clicker for this slide, but it's not connecting, so I'm gonna stand here and lecture you guys instead. But anyway, hi, I'm Ella, and I guess I'll do an introduction. I'm a senior majoring in physics, also studying astronomy, so that's me. And this talk is about the stuff I did over the summer, last summer, with the Rochester Institute of Technology through their summer RU program. So yeah. So the big title here is Active Galactic Nuclei, Big Data Edition. And effectively what the presentation is about is me trying to figure out how to efficiently analyze really large amounts of data. But those first three words are kind of big and scary, so I'm gonna give you guys a decent amount of background first. And I guess, yeah, we'll go into it. Uh-oh, it's not. There we go. So what is an active galactic nucleus? Well, it's a very, very massive, supermassive black hole at the center of a galaxy. There's supermassive black holes at the center of pretty much every galaxy, like there's one in the center of our galaxy, Sagittarius A star. But not every supermassive black hole at the center of a galaxy happens to be an AGN. It needs to be specifically, or it needs to be extra big and have a bunch of extra stuff going on. But we're going to talk a bit about black holes first, just in case anyone here isn't that familiar. A black hole is something that's so massive that not even light can escape its grasp. And they're really elusive because if you can't detect any light from them, then it's really hard to study them. This picture here is of M87. A lot of you guys might recognize it. It was in the news a lot a few years ago. It's one of the first images of a black hole. And it's actually a really amazing photo just because of how small these black holes are and how hard they are to image. But you will notice it's pretty blurry, and this just kind of demonstrates, yeah, it's really hard to learn stuff about these things. But anyway, if I were to go and zoom in on, let's say, this photo, you would have something that looks sort of like this. Can you guys see my, yeah, you can. Okay. So you would have something that looks sort of like this, because as far as the internet has told me, M87 is an AGN. You have the actual black hole at the center, but it's surrounded by a whole bunch of other structure, like this big donut-looking thing called a torus, these two really powerful jets, and this big swirling disk of gas and dust that's all falling into the black hole that's superheated that gives off a lot of light. That is actually what you see as the light in this picture. That's the accretion disk. So when astronomers want to study the light from these black holes, they're not just looking at like any old kind of light. They're looking at spectra. And what a spectra is something that astronomers use in pretty much every range of their research. And it looks something like this. So when you have various elements getting superheated, like let's say hydrogen or oxygen, they give off light, but they only give off certain colors of light or wavelengths. And that's what this image here is. It's a spectra. So this actually happens to be a hydrogen line. These two little thin ones are oxygen lines. And astronomers can look at a graph just like this and see what is this thing made of? But that's not all. The actual like widths of the lines themselves tell you a lot about the physical processes going on, and that is what I am interested in. You'll notice that there's two regions I didn't really go over here called the narrow line region and the broad line region. And the names are pretty much exactly as they sound. The broad line region gives you these wider lines, kind of like this hydrogen line, and the narrow line regions give you these like really thin lines, like these two oxygen lines here. So yeah, AGN come in many different like types and flavors. If you guys have ever heard the term quasar, that's kind of analogous. But the type I'm interested in are called Seyfert galaxies. A Seyfert galaxy is just another AGN. It's pretty bright, but they come in two types, Seyfert 1s and Seyfert 2s. Seyfert 2 galaxies, sorry, Seyfert 1 galaxies, there it is. They're characterized by having these really broad lines, like this is the hydrogen line I was talking about earlier. Whereas you can see the Seyfert 2 galaxies, actually, this same line is not as wide. But you guys should all like be really confused right now because I just said that Seyfert 1s are characterized by broad lines, but the title of this slide says narrow line Seyfert 1s, so what gives? I'm interested in something called narrow line Seyfert 1s, but all that really means is in terms of Seyfert 1 galaxies that have broad lines, they're just on the narrower side, so they're still pretty broad. But these are actually really interesting objects, and there are a lot of them that people have identified. Because the fact that the lines are so narrow actually tells us that we think the black hole mass at the center of the galaxy is pretty small, but because Sieverts are so bright, they're still accreting mass really rapidly. So things that kind of people think they might be are something like baby black holes. So that's really cool, and we want to study them. But there are a lot of those. And one of my favorite things about astronomy is that it's not that there's a lack of things to study, it's actually that I personally think there's too much data to study, and it's just a matter of how much can we sift through it and what can we draw from it. So naturally, you want to think, okay, well, how can I efficiently analyze thousands and thousands of spectra from these objects? So that was the research question I was pretty much addressing last summer, which is how can we efficiently actually analyze these very large numbers of spectra? Because I'm not going to go in and look at each spectra individually, and I don't think you would want to either. And consequently, what can we learn from them? So I guess the rest of this talk is kind of like my analysis process. And yeah, I keep going the wrong direction on the slides. Anyway, so I was given a sample of about 11,000 different objects, which I know about you, that's a pretty big number. It's like, it's more than 10, more than 100, so. And I actually had to split them into two groups just based on the different ways the spectra looked. Just has to do with like something called redshift, which if you want to ask me about that, I can talk to you later. But so I was actually analyzing samples of about 5,000 or 600 at a time. And so the thing you do when you have lots and lots of stuff that you don't want to analyze yourself is the natural course of action, you tell the computer to do it for you. And that's what this little kind of chart is here. And it's effectively the way that I had the computer analyze all these spectra. And it goes inside kind of two steps, and then humans get to analyze things. Because our goal is to have the computer break all the data down in a way that's easy for us to understand. So the first thing we do, I keep going the wrong way on the slides. Okay. Is we find 5 component spectra that the computer can use to recreate every single spectrum in your data set. What that means is that I give the computer these 5,000, 6,000 spectra, it looks at all of them, and it comes up with 5 spectra of its own that it can sort of like combine in different amounts. So maybe spectrum A has a lot of this big purple line, but not a lot of everything else. Spectrum B has a lot of everything else, but not the purple line. And using these 5 components, it can recreate every spectrum in the data set. And what I want you guys to notice is that these aren't just like random like components or spectra. Like this one's really, really tall and spiky. This one is not. And actually, these are physically interpretable. If you guys remember that graph I showed you earlier, this purple component actually corresponds to those narrow lines from before. Or the yellow and blue ones actually correspond to the broad lines from before. So not only is the data now easier to work with, but we can also actually like think about the physical components contributing to each spectrum in terms of these components. So yeah, cool. So we have all of our spectra now made really easy to work with. And then next thing we do is we tell the computer, okay, look at all these spectra and put the ones that look similar to the same bucket. Just group them. And this figure is trying to show you what the computer's sort of doing or what it looks like when it groups them up together. It's a big scary plot. I don't want you guys to get too afraid of it. All it essentially is each dot on this plot represents one spectra, and the axes aren't like the X and Y axis here are not anything like really physically that interpretable. They're just different combinations of those 5 spectra I showed you earlier. And then every spectrum is put on this plot, kind of like how it relates to those combinations of components. Don't try to wrap your head around it. I could never really wrap my head around it, but it's a way for the computer to just kind of categorize them. And then the computer goes in and says, hey, these ones are all really similar. These are really close together in terms of their components, and it groups them. So everything that's in one color is kind of a similar spectrum. So that's all the computer really did, actually. Because now we do the fun part, which is where the humans get to look at the clusters and analyze them. The machine learning part is done, which I never actually mentioned that word up ahead. It's pretty scary, so I kind of avoid it. But we get to do the fun part, which is we get to analyze the clusters. And the first thing anyone would really do when you have mass amounts of data, even if it's been broken down nicely for us, is you want to average everything together. So if I went back to these clusters, for example, I want to take all the ones in the blue cluster and merge them all together and see what I get out. And that's what this is. So I've been showing you only stuff from one of the sample, but this is both of the samples on the same slide. And these are actually the average spectra from all the spectra within each group. And I want you guys to notice how every spectrum, like as you go down, is pretty distinctly different, especially when you look at the top and bottom, like the second one. The colors on here correspond to the colors on the last graph. They have a lot of these narrow line oxygen components, like I keep mentioning. The one down here has pretty strong, broad hydrogen components. And what this tells me is that this type of analysis is actually really effective because this is not really something that's been applied to AGN in this way before, so this is pretty exciting. But it's not just that, oh cool, we can get really cool epic spectra, average spectra, but the spectra themselves are actually quite high quality. If I were to zoom in on, let's say, like this orange one here, it's from a different sample, but it looked better. This is the same one plotted against a bunch of random spectra just from its group. And you can see how noisy these spectra are in the back. Like, if I were to look at any of these, I would be able to pick out maybe 1 or 2 lines. And now it's pretty normal in astronomy that when you average things, you get rid of a lot of the noise. But because we have put these spectra through this like really kind of weird, not weird, but this really complex process, the fact that we're getting a lot of data or a lot of detail out of them is really, really promising. And if you don't believe me that we're getting a lot more data than, a lot more detail than you think, if I go to the next slide, this is that same exact spectrum just plotted against like a typical quasar spectrum with some lines overplotted. And you can actually see like we're getting this tiny little like bit of iron in here. Or we're getting this little tiny bump of helium in here. And we're getting so many tiny lines that you can actually make out, which I honestly didn't expect to see when I was first doing this. So this is one of the most exciting results for me. So the key takeaways, I guess, so far is that this is actually a very efficient method. Running this on one of my samples took, I don't know, maybe like 15 minutes, where the alternative would probably be to give your spectra each to a fitting algorithm and like have it, I know, maybe fit a function or two. And sure, maybe that takes 5 seconds to analyze each spectrum, but if you're doing that with 5,000 spectrum, that's going to take you hours. This could do this in like 15 minutes, and you still get very important valid results. Not only that, but the components are actually interpretable and the clusters are distinct. And when I say the components are interpretable, this is really exciting because not only can you just get average spectra, you can go into each different group of spectra and see, oh, this one had a lot of that narrow line component. This one had a lot of the broad lines. And the fact that the components themselves are physically interpretable is something that is very, very good for this type of analysis. And again, this is something that's not really being done except for my grad student on AGN before. So it's really promising. But the big kind of elephant in the room, which I've not really addressed, is, well, what can we learn? And my answer to that is a lot, and I'm actually not super sure yet, because the data that all of this analysis gives us, well, there's a lot of it. I don't want any of you guys to try to understand any of these plots. I put it up here solely to show you how much there was. But my current job right now is to go through a bunch of plots like these and see what I can make of it, see if I can discern any physics or maybe a cool classification or something out of it. But you have charts of like how the different components correlate with each other, the actual spectra themselves, how much of each component is in each cluster, and I don't know, there's just a lot to go through. And that's my current process once I'm not being cooked by grad applications. So yeah, actually that's all I really have for you. This is my lab group from over the summer. That's me sitting really awkwardly in the middle. And that's my PI, and that's my grad student, Lisa. So yeah, I don't know how I did on time there, but yeah, I guess thank you guys, and I can take questions.
There we go. Okay, same process as last time. If anyone
Any questions? Please raise your hand so I can see. I can start off with a question. You had a graph that
Wait, I need my graphs back up.
had a bunch of clusters on it, and there were red.
that said noise, is there a reason that you kept those on the graph instead of excluding it from the set altogether?
Okay. I don't need my slides for this one. It's not really. The algorithm itself was originally made by my graduate student, so there's not really a point to. It's kind of good to see. Okay, for context, the red ones that were labeled noise, those are just ones that the algorithm couldn't classify. We were still given data like on what the noise looks like. So in fact, we can still look and see and like actually plot all the spectra and see if it looks weird. And it's still valuable to include. I guess, yeah. Um, like it's still valuable information, and there wasn't any reason to not include it. And I'm of the opinion that more information is always better. So yeah.
Thank you. Anybody else have any questions? Yes, let me run over to you.
Thank you. Thanks for the talk. I'm curious about the slide where you talked about taking your 11,000 different pieces of information and approximating them with a combination of 5 different individual spectra. Could you talk more about how you can narrow down so much information into just combinations of those 5?
So the short answer is I give it to the computer and it has a function that does it for me. I imagine it's probably just parsing through them all and trying a bunch of different fits. When we were like, so when we're actually trying to figure out like what the right amount of components is, because I had to go through and figure out, oh, do I want 4 components, 5 components? It actually will tell you, like, it gives you information on like the error bars. Like, you can see, we had a bunch of plots of the actual like kind of errors or the differences between where like the like remade reconstructed spectra would be compared to the actual original spectra. So we can kind of just use those statistics to tell whether or not the fits are good enough, but mostly it's done by a function that I didn't dig into too much. But like there was some trial and error trying to figure out the right number of components and whether or not like they accurately recreated most of the spectra.
So you're just trying to find a reasonable approximation for each one.
Yeah, so the spectra you reconstruct are not perfect, but they're a very close approximation such that like it doesn't worry us too much.
Thank you.
Mhm.
Any other questions? Oh, okay.
Hello. It's a really great talk. Thank you. Uh, I just had a quick question, and you might have mentioned it. Sorry if I missed it. But where did you get your spectra? Like, I know, like, what, I guess, where'd you get the data? Like, where did the data come from?
Yeah. So the knowledge of which objects to use, which narrowline Seyfert ones to use, those came from, there was a paper that I was handed and that had like a catalog just of them, and then the actual spectra are from SDSS, so Sloan Digital Sky Survey, unless I butchered the name somehow. But yeah, so I mean, you can like they have just a bunch of like available spectra that you can go and play around with. So yeah.
Very cool.
I appreciate your guys' patience, by the way. We're trying to figure things out right now. In the meantime, if anyone has any other questions, or else we're kind of gonna be sitting in awkward silence for a little bit.
I can sing a song.
Oh my gosh, we have a question.
Wait, don't want to hear me sing a song? Oh.
We can sing a song after.
So you mentioned that one of your key takeaways is that this sort of data analysis method is viable in the long run. Do you know of any other sort of spots in astronomy that this sort of machine learning data analysis can be used or has been used on in the past?
Not off the top of my head. I'm sure it has been. I mean, like my grad student is doing like similar stuff just on a smaller amount of quasars, or smaller number. I don't know what the correct grammar is there, but I've not like been super into the field where I know where they've used it, but like this is, as far as I know, this is like not a new thing. Like NMF decomposition, the like splitting into 5 parts and clustering, like those are not like new techniques or anything. It's just we've not really analyzed large amounts of AGN spectra in this way before, which is why it's like pretty new and exciting.
Cool.
Abby's currently apologizing for those on Zoom, but she need not apologize.
We need jokes.
We can start a stand-up comedy.
Tell you a space joke, but it's too out of this world.
Oh, that was good. That was good.
That was a terrible joke. I don't have any machine learning jokes.
Oh, did we get it?
Look, sorry, just this.
You're not shared on
This
Zoom.
comedy set. I didn't plan it earlier. I'm out of jokes, guys.
Give me a moment. I'm so sorry. This is, again, the most vile thing.
If it's needed, you don't need to do it on Zoom. Let's say the camera's pretty good.
Okay. It might. Guys, okay, wait.
In the meantime, because I'm probably going to run out of time at the end, and I normally give this spiel at the end of our talks, I will mention that Huertes Observatory is open tonight from 8 p.m. to midnight as per usual. The cloud coverage also as per usual is not looking too incredible. I believe it's going to hover around 50 to 60 all night. You know, who knows? There might be a few open spots, maybe higher. I've seen some odd, 70, 80, whatever. But even if we cannot see the stars, we still have many attractions at the observatory, such as our museum. We give tours, and we love to have you guys, even if we can't really set up our telescopes. So we have neat panels on the walls of the museum. We do. It looks like it's working.
Well, so it'll be good enough.
You know,
it'll be. This will do. Okay.
Can we get a round of applause for Abby?
Yeah. So this is deeply unideal. Oh my goodness. Oh my goodness. Well, all righty. Can you guys see my this thing? All right. Well, oh, it worked. Oh, never mind. Oh, I fixed it. Oh, okay. Oh, we're all better. All right. After many trials and tribulations. Hello, everyone. My name is Abigail Bull. I'm a senior in physics, and I will be presenting my project on turning the Haystack 37-meter telescope into a multi-user research instrument. So
Just as a quick overview, I'm going to start with an introduction to radio astronomy. So like, what is it, how it works, and some common misconceptions. I'm then going to tell you guys a little bit about the MIT Haystack 37-meter radio telescope, which I worked with over the summer, and about some of the software that I developed. And then we'll end this by looking at some of the data that I collected over the summer, and then talk about what the telescope is currently working on. So this is going to be a mix of astronomy, engineering, and then a little behind the scenes look into the actual process of telescope operation. So just for some background, in the 1997 movie Contact, there is a famous scene where the protagonist, Ellie, in the quest to search for intelligent life beyond our solar system, is sitting by the Very Large Array and listening to radio signals from the sky through her headphones. So this idea that radio astronomy involves listening to celestial objects is a major misconception. It like kind of makes sense. We listen to the radio all the time, so like maybe radio astronomers also listen to their radio. This is wrong. This is false. So radio astronomy actually has nothing to do with sound waves. The radio waves that you might hear through your car radio are not sound at all. They're just another part of the electromagnetic spectrum. So it's just light that then gets converted into sound by your radio. And also sound waves cannot travel through space anyways because there's nothing to vibrate. You guys know the gist. So instead we're measuring these very long electromagnetic waves. So you can see here, if visible light is the size of protozoans, then radio waves are the size of buildings. So it's much, much larger. Below this, you can see the spectrum of the different types of telescopes that correspond to different wavelengths of light. And so you might notice that the designs of the different telescopes differs based on the type of wavelength of light that it's observing. And the reason for this is because different wavelengths interact differently with materials. So we need to use different kinds of telescopes in order to observe these types of wavelengths. So for example, optical telescopes like ERV will need extremely smooth mirrors or reflecting lenses in order to look at the light. Radio telescopes can use much bigger, slightly rougher surfaces in order to capture their stuff. And this is an X-ray telescope, and they actually have to use these grazing angle mirrors because otherwise X-rays will just pass directly through the mirror that you're looking at. So you have to be a little bit intentional and creative with your design choices for telescopes. So this variety of designs is not arbitrary. Again, it's very intentional. And so now that we know what radio is, let's talk about what we can do with it and why it's so powerful. So first, radio waves travel enormous distances throughout the galaxy with very little absorption. They can pass through dust clouds that would typically completely block visible light or infrared light. You can see here, this is a comparison between a view by James Webb up here and then the Meerkat radio telescope. So this is looking at the center of the galaxy, and you'll see in here, again, a beautiful James Webb image, as always. It's gorgeous. However, you get a little bit more information with the radio here. This yellow thing in the center right here, this is actually Sagittarius A star, which is the black hole at the center of our galaxy. And you just cannot see that at all in infrared. So you get a little bit more information through radio. Another great feature of radio telescopes is that they can be spread out over these very large distances and linked together through a process called interferometry. So typically, as you guys might know, the bigger the telescope, the better the angular resolution. You can look at smaller things. So using this interferometry, we can connect very distant telescopes together to effectively build a telescope the size of Earth, which is pretty cool. So radio astronomy can give us these very, very high resolution images, and it allows us to take pictures of these very, very small things like the M87 black hole. There are very, very many applications of radio astronomy. There's a lot of discoveries that have been enabled by radio astronomy. It's extremely useful subfield, and it's also really cool, but these are just a couple that I wanted to touch on here. So this brings up to the telescope that I worked on over the summer. This is the MIT Haystack 37-meter radio telescope, and it is in Westford, Massachusetts. So as the name suggests, the telescope's diameter is 37 meters or 120 feet. For a Cornell comparison, this is inspired by Hounen, it is roughly 70% the height of McGraw Tower. So if you just imagine McGraw Tower like kind of horizontally, 70% of it, that is the diameter of this telescope. So it's pretty large. The entire telescope sits within this giant ray dome, which is this white structure here, which protects it from the weather and lets it operate in a variety of different conditions. It's specifically made of a material that is transparent in radio, so it's not blocking any of the signal that comes through. The telescope was first constructed in 1964, but was rebuilt in the 2010s to have an improved dish surface accuracy. The telescope moves very quickly and very silently, so you can kind of just be standing in here like this and just not even know that it's moving around you, which is pretty cool. And usage of this telescope is split between Haystack and MIT Lincoln Labs. So what are we trying to do here? What is our goal? So if fully equipped, the Haystack 37-meter telescope would be one of the most sensitive millimeter wave instruments in the continental United States. And as we kind of touched on before, this would be an extremely useful instrument for a variety of different research fields, and would like to make this available for the research community, both for research and for outreach. However, one of the primary issues with this was that it was lacking a user-friendly control interface and a metadata management system. So my summer project was to create a more capable system for the Haystack 37-meter telescope in order to turn it into a multi-user research instrument. So what does that look like, and how do we do that? So I'm going to be very give a broad overview here. This is going to be very broad. But a radio telescope like Haystack does not run off of just one computer. It actually uses several, with each computer running its own specific job and has its own capabilities and tasks that it's given. So one computer might be the main user interface, where the observer would sit and actually give commands. Another might handle major heavy data processing. Another might handle software backend. Another one might connect directly to the telescope and issue commands about where is the telescope, is it going to hit anything, stuff like that, which is important. And all of these machines have to talk to one another in real time. They all need to be sharing data with one another at the correct time, such that we're able to properly operate this telescope. However, in this old system, the programs were not able to share data directly with one another. Instead, there was this very complicated workaround that, while functional, was not ideal. So there was no sharing of data really between these computers in one main central area, which was not great. We didn't want that. So to remedy this, I created this new Python-based monitoring and control system that allows for two-way communication between different computers. And in addition to being far more user-friendly than the previous system, it enabled the collection of metadata, so information on the telescope parameters at the time of data collection, which lets us do more with the data that we collect. And it's very, very useful. And then to populate this new system, I created a range of observational and calibration scripts for the telescope. So this is just kind of what I did. I can talk more about any of these or all of these if you guys are interested, but this is the kind of package that I ended up making. So what are some applications of this? What can you actually do with this? Let's talk about it. This will be good. So here is a solar system gallery of pointing scans. So what's a pointing scan? So a pointing scan, you point at your object and you scan across it. And you're able to see some interesting features. So for example, if you look at the sun here, you're able to see some solar emission features, which is pretty cool. This moon was taken on a full moon, so that's why you don't see the terminator line. And I promise that Mars did not vanish. It is still here and it's still a planet. It's just that in the summer, the atmosphere is pretty opaque, so it makes it difficult to see things at times. This is a Lissajous raster map. So for this type of map, the telescope will swirl around a source, taking data at each point, and then you can interpolate that data to make a larger map. And so this animation over here shows the motion of the telescope as it sweeps across the sky. And then we regrid it, and then we obtain this map. So this is Jupiter. You'll notice that there are some features in the background here. This actually is just that the atmosphere changed over the course of the time that we were taking data. What you would do about this is you would just background subtract it out. This is the Kleinman Low or Orion KL Nebula. It is the most active part of the Orion KL Nebular Cloud Complex. Orion KL is an active star-forming region and the location of a prior explosion event in the Milky Way. So within this nebula, there is an extremely strong water maser at 22 gigahertz, which we can see is this spectrum here. And for reference, the beam size of our telescope is approximately the same size as this second image, but it's centered on this blue star here. Using the new metadata functionality, we were able to create a map of this region. So this is not something that we were able to do before this project. So the center plot here is the same as in the previous slide, but each of the surrounding spectra differs in position based on a few arc seconds. And over here is the integrated intensity of a data cube using these observations. Just to note, we observe extended emission in a couple of places, but this is due to a hardware timing error that has since been resolved. Still, this map demonstrates new functionality that was not available prior to this current system. So what are we doing now? What is our current, what is Haystack doing with this system? It is currently being used to prepare the instrument for asteroid observations in the context of planetary defense. It's also being used for VLBI observations of a supermassive black hole, and it is also being used to develop hardware systems enabling next generation resolved radio images of black holes, which are all pretty neat, and I'm very excited to see what they do. So just to conclude, our goal was to bring this telescope closer to becoming a multi-user system, and I do believe we've done just that. This new user-friendly system allows computers to easily share data with one another to a central location, and these Pythonic connections allow for the collection of metadata, which is not something that was happening before. So thank you for listening, and please let me know if you have any questions.
Okay, does anyone have any questions for Abby? Oh, I see multiple now. Oh, sorry. I do not have my glasses on.
Um, could you maybe talk more about like the libraries that
Yes,
you wrote?
definitely. See, since I went last, I have the benefit of having access to my slides after the presentation. Okay, so essentially this is the way that these modules were set up is that you have a primary observing session script. So that's what this is going to be, and it's going to create a user interface for the telescope. And so if you were to use this system, it would create an interactive program for you to send commands to the telescope, run script, et cetera, et cetera. And then each one of these modules provides additional functionality to this overarching observing session script. So this one does the connections between different computers. So it takes the different computers and creates Pythonic connections between them. This one processes and plots data as it's taken. This one does position tracking, file transfers, data recording. So all of these things are very necessary for you to have. And then this one is it monitors the live weather data in the area, and then it updates the telescope's refraction parameters as it receives different data, such that you don't have to do it manually. So, yeah.
Okay, I saw a question here.
Hi.
Hello.
Do you know why, like, so like the material like is transparent radio, but do you know like why like the protective barrier around it was like built like the way it is, like why it kind of like looks like a golf ball?
So here, let me find an image of it. I think that it's created in this way such that I actually do not know why it's a golf ball. You have other types of radomes that are inflatable, but that involves pumping air into it, and then you have to have a pressure lock around the system, which is not as convenient as one might like. And so they're already building this 37-meter telescope, so I assume that they just went to the extra mile of making it something that doesn't have to be pressurized. This is just speculation, though, so I don't know that for certain.
Any other questions? I have a quick question also about the Epcot golf ball.
Yeah.
So you mentioned
Yeah.
briefly that it was to help with weather conditions, but I see a lot of these beautiful dishes that you have drawn there out and about without a golf ball around them. So what's the difference? What is the benefit behind that? And are those golf ball-less dishes still able to function in poor weather conditions?
So this is more speculation on my part. I think that they still can. Though I am not 100% certain about that. One of the reasons why you would not build one of these is that it's expensive. You have to find a material that is opaque in radio, and this is like a very like secret material that they do not release places. Some proprietary like technology that MIT developed. So you have to figure that out and you have to build it. It's expensive, and so I think that people just don't want to deal with that. And it's fine without it. It just does get weathered.
Okay, awesome. Do we have any final questions? No? Okay, thank you guys so much for coming tonight. I hope you enjoyed our speakers. If we could get a round of applause for all three of our speakers.